Thank you. The common thread among the different things that I will try to talk about in these 20 minutes or less is that gas dynamics in high redshift galaxies can be really the key to understand many interesting observations that we have been collecting in the last few years, especially thanks to JWST. And so a lot of the things that I will show are really starting from the Hansatz, if you want, the idea that the gas dynamics in early disks is really responsible for many of the interesting discoveries that are coming about in the high redshift universe. So we have learned a number of things thanks to JWST. We learned about the I-star formation efficiency in the early galaxies, which might be pointing to a different regime of feedback at high redshift. We have learned, and I will focus on that in the next few slides, that there are populations of very massive clusters, ultra-dense clusters. Someone earlier on today has already mentioned examples of them. We know that black holes are growing rapidly, even more than we thought, and already very sizable at redshift 8 to 10. And you have many cases where there is some suggestion they might be overmassive relative to their host galaxies. We know about the existence of little red dots, which of course was not expected, and we didn't have any analogs in the low redshift universe, not even at intermediate redshifts. And of course we know that galactic disks are in place very early. They might not be the majority of galaxies that have disks already at redshift 7 or 8, but we already have several examples. So already in the first couple of years after JWST came online, there were several discoveries of clumps, star-forming clumps, or massive clusters, if you want, in lens galaxies that essentially extended what we knew already about clumpy galaxies at cosmic noon. These are examples of some works that were published very soon after the JWST observations were done in the redshift regime between 5 and 7.5, even some around redshift 8. And these star-forming clumps or big clusters, it doesn't really matter how you want to call them, they have sizes between tens of parsecs to 100 parsecs, so they are slightly smaller than the ones that we knew already at cosmic noon in clumpy galaxies, but they are essentially the extension of higher redshifts of those clumps known at redshift 1 and 2. Then later, in the last couple of years, there have been some really exciting discoveries of much more extreme clusters, especially by the group of Adamo and Bradley et al., in particular in two systems, the Firefly and the Cosmic Gems. These are both lens galaxies. Thanks to the amplification of the signal by lensing, then you can really detect very small clusters. We are talking about parsec scale clusters. The most impressive example is that of Cosmic Gems, where we know about these 5 ultra-dense clusters that have masses around millions of solar masses and densities that are between 3 and 4 orders of magnitude higher than the densities of clusters in the present-day universe. Even compared to globular clusters, they are several order of magnitude higher. And the interesting things about both the Cosmic Gems and the Firefly clusters is that clusters comprise between 30 and 50% of the estimated mass of the host galaxy, which is, of course, very different from what we know in the present-day universe, where you never have such a high fraction of stellar mass in clusters. Now, in the clumpy galaxies regime, redshift around 2, there's been a lot of work by several people, including people here in this audience, in trying to understand how the star-forming clumps can be formed. And of course, one of the most successful scenarios, not the only one, but certainly one robust scenario, is that in which you form the clusters and the clumps by fragmentation of a disk that becomes gravitationally unstable, a gas disk that becomes unstable to cell gravity, and fragments. And here you see many examples of simulations. This is from our group a few years ago. This is from the group of Murnau, and this is from the group of Avishai and Nir, even more recently. There have been other additions to this scenario. For example, the role of compressed makes the picture a bit more rich, essentially in a gas-rich disk. And we've been even collecting some evidence that this might be the right scenario. There is so far only one observation of, again, in a lens galaxy at redshift 1.3 of molecular clouds with ALMA in a system which is known to have giant star-forming clumps. And these observations show that molecular clouds in this galaxy are also oversized versions of the molecular clouds that we have in present-day galaxies, and the masses are matching pretty well the masses of clusters. So that's what you expect if you form first the clouds by fragmentation, and then the clouds will turn into stars and form the clouds that you see in the UV and optical. Now, we were wondering whether this type of scenario for the formation of star-forming clumps in cosmic noon galaxies can be extended to very high-redshift galaxies and explain these ultra-compact, ultra-dense star clusters that have been observed with JWST. So what we did is we turned to cosmological simulations, but since we had to resolve objects that are a few parsecs in size, we had to apply a lot of calculations of the original volume. The original volume comes from a relatively old simulation, the massive black simulation run several years ago by Tiziana and her group at Carnegie Mellon. So what we did is we did several zooms of one of the halos, one of the largest halos in massive black, and then we applied also particle splitting to increase the resolution further, so that in the end you have a region of about 10 to the 12 solar masses that is virialized already at redshift around 8. And then you follow down to parsec scales the gas flow in the galaxies that form in this virialized region. The inventory of subgrid physics that we use is pretty standard for the code that we employed, which is gasoline 2. It's very similar to what is used in the Romulus suite of simulation, except that we don't have black holes and we don't have AGN feedback. So we have star formation, we have supernovae feedback, we have stellar winds, and many other subgrid processes, but no black holes and no AGN feedback. And so what you see as shown in these pictures of the density field of the gas and the stars is that as soon as the disk forms from the cold accretion in the galaxies in these virialized regions, it becomes immediately unstable to subgravity, essentially tumorally unstable, and fragments very quickly on an orbital timescale. And you can see here a zoom in on two of the galaxies. These are not the primary galaxy at the center of the halo, but are two companion galaxies that are a few kiloparsecs away from the center. The reason why we chose to focus on these two is because the stellar masses of the galaxies in the detected clusters by JWST are relatively small. They are around 10 to the 8, 10 to the 9 solar masses. And these are galaxies of that same mass. And you see the gas disks become unstable, and you see the clouds forming around the spiral arms in the same way as we have already seen many times in simulations of clumpy galaxies at cosmic noon. The interesting thing here, which is different, is that in the clumpy galaxies at cosmic noon, normally you see this process happening in relatively massive disks that are around 10 to the 10 solar masses. But here it's happening in relatively low mass disks. These are 10 to the 8 and 10 to the 9 solar masses. Of course, these are super compact. You can see here the sizes. This is barely 150 parsecs in size. And this is a bit bigger, 250 parsecs. But this is extremely compact compared to a galaxy at redshift 2. This is the reason why you can get fragmentation even in this very low mass galaxy. Okay? And the interesting thing is that because fragmentation is so rapid, you convert a lot of mass into stars in the clusters. Right? So the clusters form, and they rapidly comprise about 30% of the stellar mass of the after just 1 or 2 orbital times. So it's an extremely fast process. And this is exactly what you want in order to explain cosmic gems, where 30% of the mass in the galaxy is in clusters. The stellar densities are extremely high. Here you see observations of clusters and star-forming clumps at different redshifts. You see the surface mass density in stars, and here you see what we have in the simulations. And you can compare it with the sample at redshift larger than 7, which comprises also cosmic gems and firefly sparkle. You see that we are at a similar kind of ballpark value. And you can see also the masses here. Here we have also the primary galaxy included, so there are 3 galaxies for which we actually measure these clusters. You see they span a range of masses between 10 to the 5 and a few times 10 to the 7. A relatively large range and relatively high mass contribution compared to the total mass of the galaxies. Some have already formed most of the gas into stars, but others are still high gas fractions. The simulations, unfortunately, are super expensive at parsec scale resolution, so we need to stop after just a little over 10 megayears. So we cannot follow the evolution of the clusters further. And so the gas will probably keep converting into stars, Radiative feedback is not included here, but we don't expect it to be very important because of reasons that have been shown also earlier this morning and by the flash simulations of small scales, where it seems really that the feedback, even from radiation at these very high densities, doesn't have a big effect. But this is certainly something to explore further. And here you see the surface density in stars versus radius of the clusters in the simulations from the 3 galaxies that we analyzed. Cosmic gems clusters sit here. They are even more extreme in terms of sizes. We are finding sizes that are a factor of 2, 2.5 larger than the cosmic gems, but we are limited by the softening that for us is about 2 parsecs. So we expect that if we had even higher resolution, the clusters would probably be even denser and collapse to even smaller sizes. So the interesting implication of forming the clusters in this very efficient way at very high redshift in these first galaxies is that the densities are so high that if you follow what has been done by n-body simulations that try to explore the formation of intermediate mass black holes in clusters, you would immediately see that the densities are always significantly higher, but I'm talking about 2 to 3 orders of magnitude higher than the typical densities that n-body simulations require to form an intermediate mass black hole from stellar mergers in the core of the cluster, forming a very massive star, which then collapses into a black hole. So it means that we expect that all these clusters will form an AMBH. AMBHs will typically have, based on the n-body simulations, a mass of 1% the total mass of the cluster. So you do a bit of math, and you find that in a single galaxy of 10 to the 8 solar masses that we have in the simulation, we could form about 10 to the 6 solar masses worth in mass of intermediate mass black holes. What will happen then is that it will probably come down to the center by dynamical friction because of the high densities. The time scale for sinking by dynamical friction are extremely short. We're talking about a few tens of mega years, and they will be at the center. And then it will form a larger intermediate mass black hole, probably of mass 10 to the 6, 10 to the 7, if you just sum what you expect to have in each of the clusters. So this might be a very efficient way to form black hole seeds in these early clusters, acting in these early disks at redshift larger than 7. And this scenario is very similar to the one proposed by Avishai and Nick Stone in their paper last year. Just it starts from a different beginning. We have started just from the simulations results. They develop a model that is, if you want, more in the semi-analytical approach. But the conclusions are very similar, that this might be a very efficient way to form intermediate mass black holes and then black hole seeds. Let me now, in the last few slides, switch a bit topic, but using the same type of simulation that I've shown here. If we go a bit backward in time and now focus on the more massive galaxy that we have in this virialized region, we look at what happens as this more massive galaxies merges with the second most massive galaxies in the virialized region. And then we look at gas dynamics inside the merger remnant. This is the time at redshift 7.5 at which the merger has been completed. You see the gas distribution seen face on. You look at what happens closer into the center. So you zoom in into scales below 20 parsecs. And what you see is that the inflow generated by the merger has produced a very compact, flattened, gaseous system at the center, which we call a supermassive disk. It's relatively thick, but it's still rotationally supported. And this structure, which is very small in size, we're talking about a size that is less than 4 parsecs, and a mass that is as large as a few times 10 to the 8 solar masses, is very similar to what we have seen already in the past in merger simulations of high redshift galaxies in previous works, where we had even higher resolution. We could go to even 0.1 parsecs of resolution. So it's a generic feature of these gas inflows in mergers at very high redshift in systems that are extremely gas-rich, that they form a very massive rotating disk at the center that is on scales of parsecs or less, which we like to call a supermassive disk. You won't see that in lower redshift mergers simply because you don't have enough gas. And you don't have the same high density to generate a sequence of dynamical instabilities that bring all the gas to the center to even smaller than parsec scales. In the higher redshift merger simulations that we did previously, because we could go even smaller in size scales, we found that this system typically become unstable to a bar mode, and they drive gas even closer into the center. And then we try to model analytically what could happen later, and we argued that you could form a supermassive star. And actually, the configuration is very similar to what is seen in atomic cooling halo simulations by people working more in the redshift range 15 to 20 in smaller objects, of course, at higher redshift. So it's another channel to form supermassive stars, similar to what has been argued for cooling halos, atomic cooling halos, but this happens in a system that is already metal-enriched and is a much lower redshift, below redshift 10. So then, if you take the result of the simulation at face value and you try to elaborate a model based on the simulation's result, a scenario that comes about is that in these very high redshift galaxies, you might end up, after the merger, with a system that looks like this. You have a supermassive star at the center on scales of 10 to the minus 3 parsecs or so, surrounded by the supermassive disk. The supermassive star can be modeled pretty well by today's standards because there's been a lot of work in the last 5 to 10 years on supermassive stars model. And some of these models can predict even the mass-radius relationship of supermassive stars, so you can actually characterize these objects pretty well. And you also know that you have a threshold mass above which the star will collapse into a black hole. This is typically around 1 million solar masses if the star is not rotating, but it can go up to even 10 to the 8 solar masses if the star is rotating. The collapse happens through the GR radial instability, so it's a criterion that you can derive in general relativity, and you can apply that to this type of model. So story short, but let's make it as short as needed. The supermassive star, based on the models that have been produced in the literature, will live about 1 million years. After that, it will collapse into a black hole. But in this million-year time scale, you will have a system that looks like this. Supermassive star surrounded by a supermassive disk. That's what we did in this recent paper that we published, that we posted last week with former students Lawrence Wick and Chris T, who are now at Marie Curie Fellows at MBA in Copenhagen, is to model the emission from this type of system. You can model it simply by assuming that because the systems are, both the supermassive star and supermassive disk are optically thick, you can model them in two black bodies. Superimpose the two black bodies with two different temperatures. Again, from the modeling of supermassive star, you know the temperature will be somewhere in the regime 20,000 to 50,000 Kelvin. Supermassive disks need also to be modeled in some form. We did model them assuming that they are viscously accreting disks where the viscosity comes from the cell gravity, from the fact that they are transporting angular momentum by their own cell gravity via spiral density waves. Again, this is something that's been done a lot in protoplanetary disks and protostellar disks, so there's a lot of literature that you can use to model that, and that's what we did. And the endpoint of all these processes, you get relationships between the parameters that you really want to characterize, which are the masses, radii, and temperatures of the star and the disk surrounding the star. And so in the end, what we did is, assuming that this is the system in place, then we tried to see if we can actually match the spectra of little red dots using this configuration of a supermassive star surrounded by a supermassive disk. We took two examples of two spectra in the paper that are some of the most high signal-to-noise ratio spectra that have been published. We didn't model the Balmer break. We modeled essentially the V-shaped spectrum in the optical and UV part of the wavelength distribution. The lines we didn't model directly. So here what you see, you have to imagine that what we did is actually modeling the continuum part. So the red and the blue line come from matching the two spectra that we chose. You can see that we can match them pretty well. The lines we are not modeling, but we can say something about the broadening. The broadening of the lines, as you know, is one of the things that we need to explain for little red dots. Because here there is no black hole, we cannot invoke the broad line region. We cannot invoke any process associated with an AGN. So what we did is simply using this. Because the supermassive disk is a rotating disk, you can calculate the broadening based on the rotation. And it turns out that the same mass and radius that fits very well the shape of the spectra also fits very well the broadening of the line. So we get naturally about 2,000 kilometers per second line broadening from the rotation of the supermassive disk by just fitting the spectra, the V-shaped part of the spectrum in the continuum. So it seems that the model is quite successful at reproducing at least some of the most prominent features of the LRD spectra. There is more work to be done. Of course, the Malmer break has not been modeled, and will be one of the next things to do. We also computed the statistical distribution of the objects, so we made a forecast for the abundance, essentially, of systems like this, and compared it to the abundance of little red dots. This is in the paper, and I can tell you, I don't have time to show you, that also matches pretty well. Assuming that you form this supermassive star plus supermassive B system in major mergers of galaxies at redshift larger than 4, every time you have a galaxy that has at least 10 to the 8 solar masses of gas, which we say is of order the stellar mass of the galaxy in order to get the merger rate. The details are in the paper. You're welcome to ask me if you're interested. So the bottom line is we think these early disks that are gas-rich and have very short dynamical times because of the very high density and very high compactness are the origin of many of the phenomena that we are seeing now in the high redshift observation of JWST, the star clusters, the little red dots, because they are also a consequence of this very high density generating gas inflows that produce the supermassive stars at the center. And also, they might be a simple way, just the formation of the clusters themselves can be a simple way to generate intermediate mass black holes and the black hole seeds by merging several IMBHs at the center. And I'm happy to take questions.
Actually, I suggest Daisuke comes up, and we can take one quick question. I saw this one first.
Yeah, thanks for a wonderful talk. It's not just more of a comment than a question. So I wanted to comment on the Deckel-Stone scenario. So I'm going to talk about it tomorrow. And so we are currently simulating what we did with the semi-analytical model in the paper. And as you said, it's very efficient. Like dynamical friction does bring the black hole seeds to the center. It's very efficient in the absence of recoil. And we have to be very careful with gravitational wave recoil. And so with recoil, it's not as efficient as so. I'll talk about it tomorrow. And so, but what basically we are finding is that we need a mass function. So if we have all equal mass black holes, then it's basically impossible.
I agree that that's an important. This was just a general picture. I didn't go into the details.
Yeah, no, we can talk offline. And
Okay, I think let's thank Lucio again.